This time, I'm going to look at two balls, a yellow ball and a green ball. I'm going to find out what happens when they collide, when they knock into each other. That should be more interesting than having just one ball. Okay. Suppose now that I push this ball, I give this ball a push so that it rolls along the table to the right with a certain speed. Just going to give it some numbers so that it doesn't look too abstract. So maybe 2 meters per second. Okay, I'm going to be very clear that this is a velocity right from the start. So I'm going to choose my right hand side to be plus. The left hand side would be minus direction. So the velocity is therefore plus 2 meters per second. And then I have this other ball, okay, that goes in the other direction. I give it a push in the other direction. I'm going to assume that my table is perfectly smooth, right? So don't worry about the friction. And I'm going to give this ball a push at say 1 meter per second. And because this is going to the left, the velocity is minus 1 meter per second. Okay. And I also like to know what the mass of these objects are. So let's say the mass of this ball is 0.5 per kilogram, 0.5 kg. Let's say the mass of this other ball is okay, maybe 0.3 kilogram. Okay, we're all set then. We have our ball, we have our velocity, and they come at each other and they hit and they bounce back off. There are many types of ball. There are sticky balls and there are hard balls and there are bouncy balls. Now, for this example, okay, before this example, I'm going to use bouncy balls. Okay, we'll see for this. We'll see why in a moment. I'm going to use two bouncy balls. Okay, bouncy balls. Okay. Right. So what am I getting at? I am interested to know actually what are the velocities after they have collided. But that's a rather more difficult problem in physics than just using Newton's law directly for a single ball. So now we have two balls. Okay. Now I am going to write down the equation first, and then I'm going to try to understand that. So let's see. Now, so for equations, I need some symbols. So I'm going to call this ball. Let's see. I'm going to call this ball number 1 and call that ball number 2. Okay. So I need the symbol for the mass. I'm going to call this mass M1. I'll call this mass M2. I call this velocity U1. I'm going to call this velocity U2. Okay, that should be all right. Now, and I'm just going to take a quick preview just a peek into the future about what it looks like after they have collided and bounced off each other. So they come together, they bounce, and then they separate. So they come, they bounce. So when they bounce, they are in contact. Okay, they're in contact. They bounce. No, that was a green ball actually, wasn't it? Oops. Okay, I want to draw my green ball. That's the green ball. Okay. No, actually, what I'm going to do is this. I'm going to think of this as I want this to be bouncy balls, don't I? So let's imagine this, right? You have these two bouncy balls coming at each other, and when they bounce, when they hit each other, they get deformed, they get compressed a little bit, they get squeezed together a little bit. So I'm just going to exaggerate this a little bit. They get squeezed together, so they get a little bit squashed. They get squashed a little bit. So they look like this. They look a bit flattened. Yeah, that's the word. They look a bit flattened. All right, and this is why I want to use bouncy ball. I want to emphasize this this idea that when they come together, they hit each other. There is this short time in which they stay in contact. All right, there's this short time in which they become slightly squashed. Okay, and that's when they have a time of contact. And then after that, because they are a bit elastic, okay, they would rebound. They would rebound and return to their original shape. And in this rebounding, they would actually push against each other. Okay, they would push against each other and push off each other. So that's why they bounce off. So that is what you can imagine to be happening. Okay, so at this point, let's think about what happens. At this point, this red ball would push against the I'm going to use a yellow arrow to remind me that I'm talking about the force from the yellow ball at the moment. There's this force on the yellow ball that pushes on the green ball, and when this happens, there's also a force from the green ball pushing back. You know, Newton's third law, equal and opposite reaction. So they push against each other. Right. What happens then? Okay, bouncy balls collide. Let's describe this situation. Okay, so at first they are coming to each other, then they collide, and then they bounce off. Then they bounce off. Yeah, right. So when they bounce off, they return to their original shape, circular shape, no longer squashed. Okay, and they move away from each other. Okay, there we go. So that's it. Now they are on their way. Now, in this problem, we are really interested to find the velocity, the new velocity after they have bounced off. So let me call those V1 and V2. Okay, I want to know what V1 and V2 are really. So how do I find that? Now I am going to just write down the equation for them, okay, and I'm going to explain those later, how we're going to use those. The equations, right? Let me write down the equation. Right, I'm just going to write it down here. So the equations looks like this. Say something like m1 m1 u1 plus m2 u2. So those are from the values, the velocities before they collide. Okay, u1, u2. Now, so what I've done is I'm adding the momenta together. M1 u1 was the original momentum of the yellow ball. M2 u2 the original momentum of the green ball before they hit each other. So I just added those out. I just added the initial momentum. Now this equation is saying that the answer must be equal to m1. I'm just going to write down m1, m2 first. Go on to the next bit, and then I need to write down v1, v2. All right. So this equation is saying that this is the answer is equal to m1 v1, the momentum of the yellow ball after colliding, plus m2 v2, the momentum of the green ball after colliding. Right. So this equation looks a bit complicated because there are so many symbols in here. But we can describe this. We can describe this in words. We can say that we can describe this equation by saying that the total momenta before collision, that will be this part. That's the total momenta before collision, is equal to the final momenta after collision. Right? The total momenta before and after colliding is the same. Now, in physics, when something is the same, when something doesn't change, we like to describe this using a more formal term. Okay, we like to use the word conserve. Let's see. Conserve. So we use the meaning that conserve suggests that something does not change. Okay. And an even shorter way to describe this relation is to say that momentum is conserved. Momentum is conserved. So when we say momentum is conserved, okay, that there's a deeper meaning to just the three words. We really mean that the total momenta will always stay the same, okay, before and after the balls hit each other. Okay. Now there is a condition, though. There is a condition for this to be true. Now you can just imagine that if after they collide, we give, say, the yellow ball a push, then surely that must change its momentum and it's not the same anymore. So there is a condition. There must be no other force. There must be no force coming from outside. All right, when we say that momentum is conserved. So we are going to assume, we are going to say that there is this assumption, okay, that there is no outside, no force from outside, no external, and there are no external force. Well, we emphasize here the word external because clearly there are internal forces, right? When they, at the point where they come into contact, when they hit each other, they'll be applying force on each other, obviously, from this picture. So the condition is that there must be no external force. You mustn't push it, and this only happens when there is no friction. Okay, so assuming that there's no friction on table and that you don't push it, just allow them to collide freely and bounce off freely, then momentum is conserved. Momentum is conserved in the sense that if you add up the momenta before they collide and then after they collide, you add them up again, you find that the answers are the same.